This chapter is on photometry. So photometry is referring to a quantitative measurement of how bright an object is. So when you take an image of an astronomical source, the brightness that's recorded on the detector is a combination of the brightness, the intrinsic brightness of the source at the time that you're observing, plus the brightness of the background that the source is on. But it incorporated into that is any light losses that come from the light going through the atmosphere, if relevant, through any lenses, bouncing off any mirrors, entering the detector, all of that, everything the photons had to go through before it got registered on the detector. Every astronomer measures brightnesses a little bit differently. And especially when I was learning how to do photometry, it was kind of amazing to me that any two astronomers working on the same object and the same wavelength ever get the same answer. But they do. The choices that you might make differently than me at step 2 of the process are compensated for later in step 10. So everyone is doing what they think is right. And it all comes back to how the photometry is calibrated. You're calibrating back on objects of known brightness. And that's how you make sure that the answer you get is right. The shape of a point source pattern, so in other words, all of the stars pretty much that we measure are effectively point sources. And the shape of how those point sources look on the image is called the point spread function, or PSF. Sometimes are called the point response function, and technically the PSF is not the same as the PRF, but it doesn't really matter in practical terms. The PSF is huge, and there's a lot of flux surprisingly far from the star that you need to include when you're measuring the net brightness of a star or a galaxy. You have to, in order to measure fluxes from point sources like stars, you can do it in one of two ways. You can do aperture photometry, or you can do PSF-fitting. So we're going to talk more about what that means in a second. But for WISE catalog photometry that you get out of the WISE pipeline, all of that photometry is PSF-fitted. But as part of the many, many columns that you get back from the catalog, it includes aperture photometry as well, so that you have a way of checking to see if you suspect something is wrong with the PSF-fitted photometry. You have an intrinsic way of checking against the aperture photometry to check as a sanity check, basically. For Spitzer in general, aperture photometry is what works best for IRAC photometry, but MIPS is better for PRF-fitted photometry. Offhand, I don't know what all the other data are that we're using, whether it's aperture photometry or PSF-fitted photometry, but it's in their documentation. You have to go read it and find out. So what does aperture photometry mean? What that means is it's measuring all of the flux within an aperture, which is usually circular, centered on the star. But then you have to subtract off from that the flux from an annulus around the aperture, a donut shape around the aperture. And that's the estimate of the background. It is a quick and efficient way of doing photometry, but it may not be the most accurate you can do. It can lead to large errors, especially if you have a complicated background. And it is essentially impossible to do in very, very crowded fields where the stars are all packed together. When you do this, remember your pixels are square, but your apertures are circles. So you have to take into account fractional pixels. And that matters a lot with Spitzer data because the units are Megajanskis per steradian. And the per steradian is an area of the pixel. So it matters. And when you're doing aperture photometry, you often need to use aperture corrections. You need to apply an aperture correction to correct for the fact that your aperture almost certainly doesn't include all the source's flux outside the aperture. And so you apply an aperture correction to correct for that missing flux. So here's an example. Here I've got my target here. This first circle is the target aperture. And this ring here is the background annulus. And in this case, it's been carefully selected to avoid this nearby star. So the way that you do this is you sum up the fluxes from the target star inside that aperture. Then you count up the flux in the background in this annulus. And you scale it you get the median and you scale it by fractional pixels and scale it to get the total amount of background in the aperture. And you subtract off that total count from the background, that estimate of the background from the total flux in the aperture. And then convert the total number of counts you get for your target to brightness. We're going to talk about brightness and magnitudes shortly. Here's a more complicated example. Here we've got a target source, but it turns out that the PSF for this source is actually complicated. It's not just a point, it's got a ring around it too. So the aperture is that red circle that takes into account not just that main peak, but the first ring, the airy ring that comes around it. The annulus here, look at the background. The background is really complicated. So the background annulus is big and deliberately selected to be very, very close to the star to try to get a good estimate of the background underneath this source. As you see, it's highly variable and complicated. So that background annulus was deliberately selected to be very, very close to the target, but deliberately selected to be large to try to get a really good estimate of the background behind that star. Now, PSF fitting is the other way to do it. Now, the PSF, remember, is the response of the telescope and the detector to the point source. You have to remember the somewhat counterintuitive fact that the response of the telescope and the detector to any point source is always the same. Whether it's a bright or a faint source, it's always the same shape. It's just that the peak of the bright source is much higher than the faint source. Bright sources are going to show you lots and lots of structure in the PSF. The faint sources won't. So what you do is you tell the computer, I know what the shape of the PSF is. Go forth and match all of the sources in this image to that shape and tell me how bright they are. You give it the basic shape of the PSF and the computer then matches it, scaling it to each individual point source. And therefore it's able to take into account the fluxes at large distances from the peak of the star. And it can take into account the complicated structure in the background and other nearby point sources. So it can conceivably do a really good job of getting really, really accurate fluxes. This method works really, really well when the PSF is oversampled. In other words, there are many, many pixels making up the PSF. That's not the case in IRAC images, which is why IRAC photometry works better with aperture photometry, not PSF fitting. So here's an example of the MIPS PSF. This is how most bright sources appear with a standard stretch. You've got the peak of the source and the first airy ring. But when you do a different stretch, you can see the PSF is super complicated. There's multiple airy rings, and those are diffraction spikes from the struts that are holding the secondary. So here's how you do it. You tell the computer, this is the shape of the PSF I'm expecting. Go forth and take this PSF and look for objects shaped like this in the field. Then go and compare this to the target. Compare this fitted PSF to those of known objects. How much fainter is my target object than that of the known objects? Then calculate what the brightness of the target must be. So, here are the main takeaway points. Photometry is the quantitative measure of the brightness of an object. Conceptually, it's relatively simple. You're measuring quantitatively how bright something is. But getting into the guts of it is complicated, and there are many, many buttons and levers to try. There are lots of different ways to do it right, but you have to make lots of choices, and you have to keep testing along the way to ensure that you're getting the right answer. Pipelines, like all of the data that we're working with, are supposed to make all of those choices for you. Usually, the pipelines are more reliable the larger it is, and so therefore the more I trust it. So, if you're working with data from GLIMPS or 2MASS or Gaia or PanSTARRS, I trust those pipelines to have been thoroughly vetted, so I believe the fluxes that we get out of them. If you are working with data from a single paper on a single target, then you need to go forth with caution and make sure that you trust those data before you use it. However, the flip side is that those big, all sky pipelines have to work everywhere. So SEIP, for example, does not go to very faint targets because the SEIP was trying to make their pipelines work both in the relatively empty, sparsely populated extragalactic fields, but also in the very, very bright background, crowded galactic fields. So they had to make some trade-off choices. So that trade-off results in the SEIP catalogs not going very faint. GLIMPS, however, is all galactic plane fields, and so they were able to tune their pipelines to deal with complicated backgrounds and crowded sources. So they can go much, much deeper. They reach much fainter sources. So that's why you can rely on GLIMPS to go fainter than SEIP with the same data, because GLIMPS is tuned to deal with galactic fields. Now, here's a couple slides that are an aside. And this is involving some forward referencing of material we'll get to in a second, and I'm going to put these up again later on, but you'll see why I'm going to talk about this in a second. This is a slide I stole off of Twitter from Scott Cardell. He took images of stars of 6 different brightnesses to show how different brightnesses look with the same stretch. But I want to show this in particular because this is what we were just talking about. That was on Twitter, and then this is another friend of mine who was responding to him. Another thing I've seen students struggle with is that brighter stars look, quote, bigger on typical image displays based on how they map counts to a white level on the screen. It can lead to a very confusing way of thinking about brightness and size. In truth, of course, the brighter stars aren't bigger. Point spread functions are identical and only different in amplitude. That's what I was just talking about. The brighter stars aren't bigger. The point spread functions are identical. They're just different in amplitude. Hopefully that makes sense. We'll talk more about this part of it in a later chapter.